cos omega ct. We took a question from GATE paper 2003. A sinusoidal carrier, sine wave carrier, is amplitude modulated by symmetrical symmetrical square wave means carrier is sinusoidal and symmetrical square wave is message signal whose period is 100 microsecond. Which of the following frequency are present in modulated output? Options are: which of following frequency are presented in modulated signal? Options are 1110k. All options are in k kilohertz. K 970k and last option 1020k. To check all the after the multiplication with a sine wave with symmetrical square wave, what will be the result and what is the possible output frequency? We can derive expression for this. How it is possible? First question is, we have to multiply two terms. Symmetrical square wave. Fourier transform of symmetrical square wave is 4 by pi a cos omega c omega mt 1 by 3 cos 3 omega mt 1 by 5 cos 5 omega mt. In this case, it is playing role of message signal. We want to multiply with a cos omega ct. Now multiple input is available to us, means it is a case of multi-tone. If single tone means we generate frequency omega c plus minus omega m1 m. If this frequency multiply with this omega c plus minus 3 omega m, omega c plus minus 5 omega m, all these terms are presented in output because now it is case of multi-tone, not single frequency is multiplied with carrier component. Both are multiply, omega c use here, दोनों multiply किया तो क्या मिला, add and subtract. We put the value in it, fm, or fm, value of fm is 100 microsecond, inverse of it is 20 kilohertz, sorry 10 kilohertz, and fc 1000 kilohertz. All these terms in omega we can generate in frequency hertz also. No difference, only difference of 2 pi. So we can directly use, result will be fc. fc is 1000 k, fc plus minus fm 1000 plus minus 10, fc plus minus 3 fm 1000 plus minus 30, fc plus minus 5m 1000 plus minus 50. In first case answer is 1000k, second case 990 and 110. In third case 970, 1030. We can pick odd option from all the given frequency component. Now we will discuss second method, square law modulator or diode modulator. Nonlinear modulator. In this modulator, we draw diagram. Instead of using switching device here, we use non-linear device. It may be diode, transistor, any non-linear device which have 1 degree of nonlinearity, which provide 1 degree of nonlinearity, and again same type of band pass filter having at least bandwidth twice of omega. The of char- characteristic equation of nonlinear device is which have second harmonic term, higher harmonic term is not there. We use this nonlinear device. This nonlinear device can be realized in this way, which can be realized in this way. We apply this addition term on this expression, we will get desirable AM waveform. So first we applied a V in, V1 is our input, V in is our input. From here I apply MT plus A cos omega CT plus B MT plus A cos omega CT whole square. I expand this, I expand, after expanding I got this term can't be passed through band pass filter. This procedure is very important. This procedure repeated asked in the gate examination. Lot of frequency component generated through a process, and after passing through a band pass filter or maybe a low pass filter, after passing through a filter, what will be the result? The procedure is very important. This term will be selected. This term not selected because m square, m means message signal bandwidth, it is band limited signal. M square means square of it. By squaring this term, this is spectrum in this way, start at 0 and band limited up to twice of omega m. This term also can't be selected. This term omega m plus omega c mod of this plus minus omega m. This term is desirable multiplication also selected. Double of omega c not selected. Means we are sure about generation of m. We move ahead. If m square I want to draw, this term again multiply with this term, means in time domain, in frequency domain convolution result may be twice omega m plus twice omega m plus minus same type of signal multiply with itself, result will be this. Desirable result is AM waveform. Now we will discuss a question of gate 2003 2 marks question. A DSB SC signal is to be generated with a carrier frequency FC 1 megahertz using a non-linear device with input characteristic V out equals to A naught V in A1 V in Q, where A naught and are constants, and output of nonlinear device can be filtered by appropriate band pass filter. Let V in equals to AC cos 2 pi FC dash T MT, where MT is message signal and FC dash is 1 megahertz. Then calculate FC dash in megahertz. In the question, we are following some procedure. A DSBSC signal is to be generated. We want to generate DSBSC signal with carrier frequency 1 megahertz. 1 megahertz is our carrier frequency. By passing through a non non-linear device. Input output characteristic mentioned here. Input of this non-linear device is given to us. By applying this input to this device, we get result DSBSC. Difference between double sideband suppressed carrier and AM is DSB with carrier FC. If carrier is absent, this is DSB SC. Means in AM, in short, we say it is the AM waveform. A multiplication and one carrier is additional added with multiplication. It is called AM. If it carrier is suppressed by any idea, it is converted into DSBSC. We want to generate DSBSC via non-linear scheme. How it is possible? For non-linear scheme, we want to generate DSBSC. V out equals to A AC dash cos 2 pi FC dash T plus MT A1 AC dash cos 2 pi FC dash T plus MT whole cube. Then we solve this, expand this expression. With expansion, we get these terms. Out of this term, after getting all the term, we pass through appropriate bandpass filter for DSBSC, double sideband and suppressed carrier. For DSBSC, basic formula for DSBSC is DSBSC, carrier and message signal. In this term, FC dash, it is not carrier, not pass through this. It also not pass through this. It is cube of particular frequency. It is not pass. Only these two terms are point of interest. Out of these two terms, one term is desirable component. In this term, message signal square is available in output. We require only message signal. Means this is not our DSBSC, is this one. In this component, FC dash cos can be converted into cos square theta, converted into cos 2 theta 1 minus, can be converted into cos 2 theta. Means twice of FC dash is equals to this component playing a role of carrier frequency. Means its frequency is directly equal to carrier component 1 megahertz. We can finalize 1 megahertz, 0.5 megahertz. Our answer is 0.5 megahertz. We start demodulation of AM. For demodulation, we discuss two ideas: asynchronous method asynchronous demodulation and synchronous method of demodulation. Asynchronous method means non-coherent. Synchronous means coherent method. Synchronous means demodulator generate a carrier at local end, at receiver end. Demodulate without locally generated carrier means asynchronous method. Without locally generated carrier at receiver. With locally generated carrier at receiver is synchronous method. First we discuss asynchronous method, non-coherent method. Because in AM along the transmission, in AM expression along the transmission we transmit additional carrier, so local generation of carrier is not desirable feature. So we use two idea to demodulate: square law demodulator and envelope detector. Square law demodulator and envelope detector. Linear diode detector. Linear diode detector. Square law demodulator and linear diode detector. First we start square law demodulator. In a square law demodulator, AM wave is applied to non-linear device and at the output LPF, low pass filter. For demodulation purpose we use low pass filter because we want original message signal here, AM waveform. For modulation purpose we use band pass filter because via modulation low pass signal converted into band pass signal. Via demodulation band pass signal is converted into low pass signal. So we apply input here is A cos omega ct. Nonlinear device expression is plus BVN. After application of this input, we get this expression. Instead of VN, we put, by putting input, now we expand these two expressions. With expansion, we get 5 term. For low pass filter, this term can't pass because cos square term has 2 term. 1 plus cos 2 theta upon 2 is cos square theta. Means this term has some DC component. DC component pass through low pass filter, otherwise remaining not. DC component is A by 2, otherwise it is not pass. What about this term? Again M square term, M term. This term higher frequency term not pass. This term is multiplication between MT and cos and additional some term. This is also not pass. These two terms are under consideration. These two terms are in consideration. In both the term cos square term, we expand with cos 2 theta. Out of these two terms, this term is multiplied and eliminated. Our useful term is Ka square A square A M square T Ka M A square MT into A. Both are useful term for us. M square term also enter with message signal. This is the desirable component. If we scale this amount, actual amount is MT upon 2 A upon K. some scaling amount is again with message, we got this result. Along with this result we get this component also. This component treated as interference because m square, if empty spectrum is shown as, then empty multiply with again empty in frequency domain, both are convolute, result will be twice omega m, twice omega m minus omega m minus omega m minus omega m. We are using filter of omega m, means this term twice omega m interfere with this term and result is interference. So we can calculate minimum SNR value for this signal to noise ratio. Desirable component is known as signal, non-desirable component is known as noise. Desirable component coefficient is k m is sorry, we divide both the component, empty cancel with this and remaining term also cancel with all the term, on only k is remaining. 2 upon k empty means mu. Mu should be less than 1 to generate, to demodulate AM waveform through square wave demodulator. Now we will discuss envelope detector, very important topic. Now we will discuss envelope detector. It is also known as linear diode detector. Circuit for envelope detector is, circuit for diode envelope detector or linear diode detector is drawn as, there are two type of cycle: charging cycle for capacitor charge and discharging cycle for discharge of capacitor. There is large value of load resistance RL. Basic expression for AM waveform is A cos omega ct 1 plus k mt. This term is known as envelope. This term is known as envelope. We want to fetch this envelope. Envelope of AM signal carry the message information. It carry message information. We want to discuss some points about envelope detector, very important points. It is very important topic. Alternate year one, minimum one question in gate. It is a peak detector circuit. Detector circuit means whatever applied to it, it give its peak value. If I apply triangular wave on it, it give peak value of the triangular waveform. Where we discuss, two type of charging and discharging. RSC is charging time constant, which is very small, very small. Charging time constant is small due to forward resistance of this diode. RLC is discharging time constant, discharging time constant, very large. When we apply input on it, output of envelope detector, because it is peak detector circuit, tan cos 2 pi fct, result will be 10. AC cos 2 pi fct, result will be AC. If we apply e power minus t cos omega ct, result will be e power minus t. If we apply a cos omega ct plus b sin omega ct, result will be root of a square and b square. A 1 plus k mt cos omega ct, a 1 plus k mt. This is the envelope for AM waveform, where ka equals to 1. Output of envelope detector is a ka mt, means our output is a plus mt. Due to this is a DC term, we are considering DC term 0, because of in demodulator lot of amplifying stage, amplifier stage are used, so output is in receiver block diagram lot of amplifiers, pre-amplifier, etc, etc. So it is power amplifier, it is eliminated due to biasing. So result is this. Point number 2 for envelope detector is during discharging or charging. First we during charging, third point is during discharging. Discharging RSC 1 upon FC and 1 upon FC RC 1 upon FM, twice of, or 1 upon bandwidth. These two conditions are very important. During discharging and during charging, we draw an AM waveform and apply envelope detector on it. We construct an AM waveform applied to envelope detector during charging cycle. This sine wave rotate in this way. At this point, when we are at this point, during this point in the circuit, capacitor is charged. Capacitor should be charged as fast as possible to next cycle to become, means charging time of the circuit should be less than 1 upon fc, because this time is 1 upon fc. This time should be, charging time should be so small as compared to 1 upon fc. So before next cycle to come, this capacitor is charged up to this level for charging purpose, means this charging time should be less than 1 upon fc. 1 upon fc is difference between two cycles, time for difference between two cycles. For discharging time constant rc should be greater than 1 upon fc. Discharging time should be greater than 1 upon fc, means time between two cycles rc should be greater, means before next cycle come, this peak should be, during discharging this peak should be follow message signal. If it is not, if 1 upon fc is greater than RC is less, RC is so fast discharging, means RC discharge in between two cycle, means it can't cop up the peak of next cycle during discharging, it drop in between, it means it can't cop up. We want to follow the envelope of the message signal, AM signal. So this is not desirable condition. Desirable condition should be FC should be less than RC, and second condition come from this peak and this peak, half of it means at this juncture 1 upon fm by 2, 1 upon twice fm, it is the bandwidth of modulating signal, half of it, it is not so much slow discharging, so it can be skip all the peak and drop at this level. RC is not too much slow from 1 upon twice of fm, so it can skip all the peak within the half cycle. So these two conditions come from charging and discharging. Very important condition. Alternate year we get one minimum question from envelope detector. Two more conditions. Condition number fourth. Envelope detector work for undermodulated waveform only. For undermodulated. And fifth, for overmodulated. Overmodulated. If someone apply AM waveform, so received message signal is a rectified version of message signal. It is rectified version of message signal. We can't apply overmodulated waveform on envelope data. If we apply, we get rectified version of AM message signal. Take a simple question. If message signal bandwidth is given to us 1 kHz, carrier frequency is 1 MHz, calculate appropriate value of RC from following options: 1 microsecond, 20 microsecond, 250 microsecond, fourth 500 microsecond. As per given data, RC should be oscillate between these two values, 1 mega m and 1 upon 2 kilo. 1 mega means 1 microsecond. RC should be greater than 1 upon 1 kilohertz means 2 kilohertz. 2 kilohertz means 500 microsecond. RC should be in the range of this. So we have to take appropriate answer. In this case, appropriate answer is 20 microsecond. This option also in the range of this. Sorry, we can took 2 kilohertz here, 4 kilohertz here, and 250. Data is missed now. I repeat, message signal is 2 kilohertz, carrier frequency is 1 megahertz. Then I put all the values and range within this range. What is suitable RC? Suitable RC is 20 microsecond.